Hello, my name is Sankeerthana, and I'm here to share a bit more about my final year project titled Blackout, an augmentation technique for occlusion handling in pedestrian detection. So this is the agenda for today. So I'm going to start a bit about talking about pedestrian detection, which is a computer vision technique that involves identifying and locating pedestrians. It uses both classification and regression. The applications of this are very wide-ranging. It ranges from autonomous driving to all the way to assistive technologies for the visually impaired. So the objectives of this project is to improve the YOLO-X performance in terms of its accuracy. And we do this by tackling the challenge of intra-class occlusion amongst pedestrians. So the scope of this project is basically it involves working with existing YOLO-XS and YOLO-XM models to improve accuracy. And we do this by using the open source YOLO-X code, which is written in PyTorch and Python. We also use TensorBoard to visualize the training process, and OpenCV and Python are used to code out the proposed Blackout algorithm. So the YOLO-X model is actually a model from the YOLO series. It was developed by researchers at MEGV, which is a Chinese technology company, and was first introduced in 2021. The makers actually made a few changes to YOLO-X, which allow it to be an anchor-free model and achieve higher accuracy as well. So these changes are anchorless detection, Simota label assignment, decoupled head, and strong augmentation techniques such as mosaic and mix-up. So the existing challenges in the field of pedestrian detection are that pedestrians who appear farther away from the camera in the image are very small in scale. So because of this, the model has a tough time trying to learn features from that. And the second challenge is that due to the data collection process, because this is very closely related to autonomous vehicles and autonomous driving, data is usually collected by keeping a camera on top of the car and then just driving through the streets. There are bound to be blurred images in the data set, but these are very hard for the model to learn from. So the third challenge is that the accessories and color of attire, such as caps and hoodies, may actually hinder the model from learning correct features of the pedestrians. And the fourth challenge is occlusion, which we will be talking about more in detail. So here, these pictures kind of actually illustrate the challenges. The first being small-scale pedestrians, second being hoodies and caps, occluding the model from learning, and third being blurred images. So occlusion is of two types. There's interclass and intraclass. So interclass occlusion refers to pedestrians being occluded by objects from another class, such as trees and signals and buildings and walls and so on and so forth. So here we can see in this image that a boy is actually almost 90% blocked by a tree. And the intra-class occlusion refers to pedestrians being blocked by other pedestrians themselves. So in this image, we can actually see three men who are walking, but the second two men are very occluded by the first man. So there have been prior work that has aimed at tackling this problem of occlusion. And one such method is cutout, which is a data augmentation technique that involves randomly masking out or cutting out regions of inputs. So essentially what they do is they just impose a black square on top of certain regions in the image. And the size and the location of the cutout regions are randomly selected. So the goal is to actually direct the learning of the model to learn more robust features so that it relies on the non-cutout regions. So the proposed algorithm, Blackout, is actually an enhancement of the existing cutout augmentation technique, where what Blackout does is it actually calculates the intersection over union values or the IOU values of the ground truth bounding boxes, and it blacks out the intersection if the IOU values falls within the certain threshold, like for example from 0.2 to 0.5. So what this ensures is that the learning process of the model is focused on the outlines of the pedestrians only. So it also encourages the model to not only focus on the outlines of the pedestrians, but also on the parts that are visible. So the model can detect pedestrians even when there's occlusion. So the motivation behind this comes from the problem of intra-class occlusion and the fact that cutout randomly allocates these blacked out region, but Blackout actually has a strategy. It uses IOU values. Yep. So this is the implementation where we actually calculate the IOU values, and if it falls within the threshold, we black out the intersection and we add it um, in the training set, which is then trained on the YOLO X, and we get our detections. So we actually conducted two experiments. The first experiment and the second experiment both are conducted on the pen, foot, and pedestrian detection data set. The data processing involved actually involves just converting the images from .png to .jpeg and labeling them in the Pascal VOC template using the label IMG tool. So the first experiment, our aim was to see if the accuracy of the YOLO X would increase if we added Blackout to the default strong augmentations of YOLO X, which are Mosaic and Mix-Up. So they were in the training set, there were 25 images that had Blackout, and the augmentations total in use were Mosaic, Mix-Up, Blackout, and random horizontal flipping. So from the results, we can see that there is an overall increase in both the models, but there's a higher increase in YOLO XM. So this is also reflective in the inferenced images, where we can see that in YOLO XS, the bounding boxes are not very tight and not very accurate as well. But for YOLO XM, it is very accurate. And in general, YOLO XM predicts with a higher confidence. So in the second experiment, what we did was we were evaluating whether the accuracy would still increase if Blackout was the only strong augmentation implemented. And as we can see from YOLO XS, there's not much change in accuracy. In fact, there's a slight downfall. But for YOLO XM, there's a whopping 13% increase in accuracy. So this can also be seen in their inferenced images, where YOLO XS has actually not detected a pedestrian over here, and it has also misdetected a cyclist as a pedestrian, while for YOLO XM, these errors are not seen, and it's pretty much accurate. So from both the experiments, it can be concluded that Blackout works the best as a standalone augmentation on larger models. So the limitation of this project is that most of the data set contains images taken in the day and in proper weather, in normal weathers. But to make our model more robust and domain specific, we can add images that have been taken at night or in other weather conditions and lighting conditions, such as rain and snow. Future work includes implementing Blackout on the feature maps of the layers directly of the feature extractor so that we can also see how this affects the accuracy. So this leads to the end of our sharing, and thank you so much for your time.